Okay, Assalamualaikum warahmatullahi wabarakatuh and good day everyone. So I will show you a simulation of an activity that could be done in the lab, but of course after PKPP. Okay, but so since you cannot go to your school and you have to be at home, so I'll show you this simulation so you can carry out this simulation on your own. Okay, now the experiment setup is as shown, but if you are in the lab it should be slightly different. Like you might need ray box, okay, and glass block, and white paper, pencils, and protector. Okay. So let me just remove the protector. So this is an example of protector, the round sheet. Now, okay, let's start. Okay. So this is the incident ray. This is the refracted ray. Okay. So this is the angle of incidence. So let me just reduce. Okay. Now let's take this angle. So this is the incident ray. This is the refracted ray. This is the incident angle. This is the refracted angle. Remember, the angles must be measured from the normal. Okay, not from the surface. You will be wrong. Okay. Now, so I choose the refractive index as 1.50. Okay. Now make the incident angle is around, okay, I'll choose this one, around 33.8 degree. So what we have now is just a phenomena of refraction. So incident, so this refract. Okay. Now we know that for refraction, the refracted ray, this one, is further away from the normal line when travels from high optical density, from here, to the lower optical density material. So for example, as this situation, so from the glass block to the air. So it knows, okay, the angle is further away from the normal. And the bending, why is the bending? Kenapa dia tak straight? The bending is because the light is faster here in the air, but the light is slower in the glass block. Now we are going to increase the incident angle. This one, we want to increase it so that it becomes somewhere around 41 degree. Okay, now, so, oh yeah, but before that, okay, so from here you see that when we increase the incident angle, the refracted angle will be increased as well. Now we look at that, what we have. So this is no longer a normal refraction. So this is a refraction, but we have a special name for this phenomenon. Okay, now when the angle of incidence is 41.8 degrees, so here is 41.8 degree. Okay, look at the refracted ray. So this is the refracted ray. So what's the angle? It's 90 degree from the normal line. So when this happens, the incident angle is called the critical angle. So this is the critical angle, not the 90 degree one. Don't get yourself wrong. So that is common mistake lah. Sometimes most students think the angle of critical is this one. No, the angle of critical is the incident angle. Okay, so this is the phenomena of critical angle, not yet total internal reflection. Now what happens if we increase the angle further? Now the angle is more than 41.8, which is 43.1 degree here. 30, 40, 41.1, 43.1 degree. So we no longer get critical angle phenomena. We don't call this angle as critical angle. So we just call it as incident angle only. But this happens, okay? So the refracted ray is reflected back. So this phenomena is called as total internal reflection. Okay, so this is total internal reflection. So what is the condition of this total internal reflection phenomena? So the condition is, for this to happen, light must travel from dense material to less dense, and the incident angle must be greater than the critical angle. If it is equivalent, so you get this phenomena. If it is less than critical angle, you get the normal refraction. Okay, so that are the two conditions. You must know the condition. Okay, that is always asked. Okay, let's go back to critical angle. So this is critical angle. Now we have refractive index 1.50. So the critical angle is 41.8 degree. What happens if we change other block? I mean, what happens if we increase the refractive index? Yeah, when you change the medium, so you are changing the refractive index as well. So now let's say we increase this one, becomes 1. Let's just take 1.6. Oops, slightly higher. Okay, lah tu. Okay, 1.61. The refractive index is higher. Okay. When we increase the refractive index to 1.61, the critical angle will be, okay, so this is not critical angle, so let's find out what's the critical angle. Now, you see the critical angle becomes 38.5 degree. Okay, okay, let's try another one. We increase further, 1.7 almost. Okay, now this is no longer, this is not a critical angle, this is total internal reflection. So let's find out what is the angle of the critical angle for this refractive index. Okay, so the critical angle is 36 degree. So it's even. You want to experiment with more? You can do experiment. Okay, find the critical angle. Okay, so we have done 4 examples here. If you are in the lab, you can do the same, just the same thing. So the angle of incidence is 31.6 degrees. So you see the refracted ray is on the boundary, which is 90 degree. So this is critical angle. So we can conclude that the critical angle depends on the refractive index. Okay, the higher the refractive index, the smaller the critical angle. So refractive index also tells us the optical density of a medium. Okay, here are examples of phenomena of total internal reflection. So we have looked at the simulation. So now let's look at the examples. Yay! So now the first one is mirage. Okay, if you ever come across to this situation, if let's say you want to go back from your hometown to the village, or you want to travel, okay, when you travel by bus or usually by car, if you still wake up, you don't sleep in the car, you will see a wet spot on the road. Okay, but there is when you reach there is no water. So a wet spot mirage is produced when light from the sky is refracted by warm air near the road surface. So the road becomes very hot during a hot day. So the air layer near to the road becomes warmer compared to other air layer. Okay, so the sky is refracted by warm air near the road surface. Okay. Such a refraction also enables us to perceive heated air rising. Okay. This, although air cannot be seen, the refraction in the turbulent updrafts causes the radiations to be light passing through. So of course, the index of refraction varies with temperature. Okay? So actually what you see on the road is not water, but it's actually the reflection of cloud. Now here, what is this? So these are decorative lamps. Okay, so decorative lamps use fiber optics. So you see this one, fiber optics on a fabric, okay, cloth, okay, fabric. So this one, fiber optics, decoration lamps lah, lamp. Okay, an important use of the flexible fiber bundle is to pipe light. Okay, light is piped to hard-to-reach pieces. Okay, light may also be transmitted down one set of fibers and reflected back through another place, so that an image of the illuminated area is seen. So if you look at this, light source is just this one here, far from the way you want to see it. Okay, but light is reflected all through the way and then until reach there. Okay, so at the back of mine also has reflected ray also. Okay, right. Decoration light carry coloured light to different parts of the decoration and let it shine out different directions. Okay, so like for example, a fabric designer, they want the fabric to illuminate or to make costume, for example. So the light source is at the back or somewhere else. Only one light source, but the light can travel to other direction. Okay, so if you use fiber optics in making of such fabric, so we use less power, okay, and we less dangerous lah. Okay, so fiber optics also just now we talked about the illumination. This illuminated area might be a person's stomach or a heart or intestine, for example. Okay, so these are used in medical applications, just like you see now on the screen. Okay, so the medical officer or the doctor is explaining the patient. So it uses endoscope. So endoscope is put into the body. Okay, so the light or information in the form of light travels all through the way, reflected. Why is it reflected? Okay, we have learned that one. So this is to observe the sun. Okay, so this is what you will see on the screen. Okay, so if you can see in this diagram, a fiber optic bundle helps between a person's fingers. The ends of the fibers are lit up. Okay, you notice here. Okay, lit up. Although there's no them. So it's lit up because of transmission of light by multiple internal reflections. Okay. This is not an advertisement, okay, but I use these pictures. Okay, fiber optics is also used in telephone communication. Okay, electronic signals in wires are replaced by light signals or sometimes through infrared pulses in the fibers. Okay, so you usually use to see these advertisements. Maxis fiber internet, cell phone home, fiber. So actually, the electronic signals change to light signals. Okay. So this enables long distance communications to occur quickly and cheaply. So yes, it's cheaper. A glass fiber is much cheaper than the price of copper wire. That's for information. And easier to maintain. So the fibers can be drawn out thinner than copper wire. More fibers can be bundled in a cable, so for a greater number of cells. Okay, optical fibers can carry much more information than copper cables. Okay, so when light that is incident on the edge of a transparent tube exceeds the critical angle, it is internally reflected along the tube, which acts as the light bulb. Okay, communication. Okay, I want to go back to. Okay, this is binoculars. So these binoculars employ corner reflectors with total internal reflection. So there are two pieces of prisms here. Okay, so the object, light from the object is reflected again, and then another one reflection and goes to the observer's eye. What is this? So this is a diamond. Okay, so we mean like this. Okay, why is diamond looks very nice, why is it sparkling? Okay, it's because of the reflection of light. Okay, reflection of light. Okay, when light pass through the diamond, so it will be reflected. That's why. So what you see is actually the reflection of light. So diamond, the expensive ones, are cut at certain angles so that it will reflect most light.
Okay, so that's all. So hopefully so interesting, right? You learn a lot. So you actually you can apply the principle in our daily life. So see you again.